Morning, everybody. Thanks for coming out on this sunny San Francisco morning. The idea behind the Small Data Conference was credited to actually Bob, the CEO of Weaviate. We were at a VC conference somewhere, and he said, "What do you think of like doing a small data conference? Everybody talks about big data conferences and runs around, but they're always so serious. Like we could do something fun and something a little bit different." And we started thinking about it and being like, I bet we could get a really good class of speakers. People who would just love to be able to talk about what is possible when the scale of your data isn't actually the most important feature of it. Like, well, if we can get really good speakers, I bet we could get really good attendees, people to come out, really interesting folks who kind of believe in this small data mission and come and join us. And so, I think it was about a year ago, and the idea behind this was born, and this is the first one. We don't know if there's going to be another one, so if you are enjoying it, please let us know. And we do actually already have some people who are speakers actually that we didn't have space for this time, or weren't able to make it, and we're like, we'd love to do next year. So maybe we will do next year, but only if we get kind of enough excitement and feedback from people. So today I'm going to talk a little bit about kind of the background around small data, and its foil obviously is big data. It's an area that I've been working in for the last 15 years or so now, and something I've been sort of interested in for a long time. Of course, I was sort of on the other side of the equation for several years, but it really did start out there, like when before big data was a thing. There was a real problem. Data sizes were growing, and people had a hard time actually being able to handle those. And one of the problems, and before I get into that, I actually want to talk about what is big data, because it helps to actually have a shared definition. And people kind of bat around various ideas about what big data means, but to me it's anything that's too big to run on a single machine, because that's when you have to do things differently. That when you have to sort of change how you're performing your computations, how you're storing data, how you're moving data. And in a couple of examples, from the early days, I had a job interview once, and they said, well, part of the job interview is sort of this take-home problem, and I want you to process this and get some result from this, giant CSV file it was 1 gigabyte, and that sounds like kind of laughably small these days, but actually I wasn't able to get it to run on my laptop, and they gave me like a sample of it that was like only 10%, so I could run it on my laptop. Now that company was a small startup company. They had 20 people, and but they were processing huge amounts of data per day. At that time, 100 gigabytes of data was a massive amount of data. They had their pixel, so they basically had 10% of the internet traffic had like their advertising pixel on it, and so they were able to get logs from 10% of all the internet, and that was 100 gigabytes a day, like fantastically large amount of data. And so one of the lessons that I learned from working at that company was like, hey, even small companies have big data. Big data is going to be a thing for everyone. And so the problem that we were seeing was really that the costs of hardware were nonlinear. So if you needed, if you ran out of space on your single machine, your single server machine, and you needed to be able to put more disks in it, you had to buy a bigger machine, but that machine was a lot more complicated and it was a lot more expensive. So it wasn't twice as expensive, it was 10 times as expensive. And then when you ran out of, you weren't able to stuff any more disks or memory or CPUs into that machine, you had to buy the next one, and that was 10 times as expensive. And the next one was 10 times as expensive. And you got to a point where actually you couldn't even grow any bigger. And a lot of companies were making a ton of money selling these incredibly beefy hardware systems. So Google sort of turned this whole thing on its head, and I think they ended up kind of breaking people's brains in how they thought about about data and scaling with a series of 3 papers that came out. The first one was Google File System. Google File System kind of lets you have like a storage area network or giant scalable storage system built out of commodity parts. So built out of inexpensive pieces, so you didn't have to buy those really expensive machines. Then MapReduce came out, and they argued that you could separate every computation into a series of 2 steps, a map step and a reduce step. And if you did that, then you could scale those out really, really efficiently, and they were able to do so at Google. And then lastly was Bigtable. And Bigtable is sort of, hey, you can have a scalable database as long as you kind of squint and kind of don't really need some of the things that a database usually needs, like ACID transactions, consistency, et cetera. But people were running, banging their heads into the wall, and these things all sounded like good outcomes. And all this stuff got wrapped up by some folks, I think at Yahoo and Doug Cutting, and they kind of turned that into the open source version of that was Hadoop, and the open source the Hadoop version of GFS was HDFS. The open source version of MapReduce was kind of the main Hadoop execution, and then on the database side, on the Bigtable side, was effectively H-based. But these really just kind of changed how people built and scaled systems. And so, if you think of it in a little bit of a kind of a stylized architectural way, instead of buying single nodes that were bigger, you just sort of added more machines. And so like a medium cluster, essentially had 2 of these boxes, and so $2,000 boxes was $2,000. A larger one that had 6 was just $6,000. So it helped incredibly with cost, and then also you could effectively scale this up infinitely. So the advantages were you get linear scaling, you get fault tolerance, because actually one of the problems. Actually, if you have one of these $100,000 machines, is what happens when that $100,000 machine fails. Then you need a second $100,000 machine for a backup. The nice thing about this is any of these machines could fail, and you could just replace them. And they were really good at throughput. And of course, there was a trade-off between throughput and latency. So you could get a lot done in a certain amount of time. You could send a lot of data through these, but latency was bad. So if you wanted to get an answer, it might take you minutes. And the other thing was complexity. There was a lot of additional mechanisms that had to go along with this, tens of millions of lines of code to make it actually work. This introduced the big data tax. And the big data tax is sort of defining as the overhead of running big data systems. And the areas where they show up are latency, things slow down, system complexity, there's a lot of more moving parts. And while this, in this example, it did reduce some of the costs, as we'll see in a little bit, it doesn't actually change the cost structure because you're still doing the same amount of work or even more work. So for an example, what the Hadoop big data tax is, I won't go through all these, but there's just a bunch of stuff that has to happen that's not actually doing the work. So none of these steps are doing the work that you're trying to solve. They're basically just all these sort of machinery pieces. And what that would mean is, for a Hadoop job, it would take 1 to 10 minutes. So you might say, well, nobody's using Hadoop these days, and Hadoop was the bad old days, and it was sort of this dead end, technological dead end. And so Google came out with 2 new papers, Dremel, and Dremel became BigQuery, and Spanner became Google Cloud Spanner. And these really said, hey, we're going to take some of these underlying systems, the same ideas, and we're going to actually build things that look closer to what you expect. Like Spanner is an actual real ACID transactional database. Dremel became kind of an actual cloud data warehouse. But we also added a new tax. So when you move everything to the cloud, there's a cloud tax, which is essentially, maybe it's not as big or as big of a deal, but everything you do, you have a transition to the cloud and back. So you're adding 100 milliseconds. It may not seem like enough, or a lot, but in in the transactional database world where you're kind of used to doing thousands of transactions per second, it does add up and it makes certain architectures not work anymore. And so in BigQuery, there's just tons and tons of pieces inside BigQuery that are all these like microservices, and all of these things can fail and they roll out independently, and so there's a complexity cost. And then, at one point, the minimum query time on BigQuery was 1.5 seconds. It's much faster now, but as just sort of an example of the kinds of things that happen when you have to put all these pieces together. And then, of course, the big data tax didn't go away. The fact that you had to deal with all of these like complex distributed systems was still around. It cost, often seconds, and there was also the complexity cost in the lines of code. So one of the really, really important things in these scaling systems, in these big data systems, was the separation of storage and compute. And in the early days, Snowflake used to basically just advertise, and their sales pitch was like, we've got separation of storage and compute, and that's all you need. And they claimed to have invented it. Then we were like, well, you did it 2 years after we did it in BigQuery. And then some other people like, I think IBM were like, no, actually we've been doing this for like a decade. But regardless of who actually invented it, these sort of modern systems rely on it very heavily. And there's a couple of interesting points. So first of all, like, once you separate storage and compute, you basically throw all your storage in this giant, almost limitless object storage. And so kind of the example there is S3. You don't really have to worry about how much data you have on S3. It all just sort of works. Now, the compute cluster, there's some interesting things that then happen. Is that big data from the scaling perspective, the storage tended to grow faster than the compute did. The requirements that you needed to store the data were a lot larger than the requirements for the computation over data. And this actually is where the sort of the seeds of the, hey, maybe we don't need big data systems anymore, grew out of. So anyway, I bought the big data thing hook, line, and sinker. So I was at this startup company, Mindset Media, and was, like, yes, we've got big data, so everybody's going to have big data. Everybody's going to be Google scale. That may or may not have happened, but I was running around the world kind of giving talks. And one of the things that I would do is I had this thing that I would do. I would run a petabyte query against BigQuery. So I would scan this whole petabyte. And that was pretty revolutionary at the time. I think the first time I did it, I got, a round of applause, like in mid talk. That doesn't happen a lot in data talks. Thank you. But that was pretty cool, and I'll get back to that in a second, because pretty much once these systems started being coming out, you started to see some cracks. And so, for example, if you were going to pick a transactional database, what would you use? Anybody? SQLite. SQLite is great. Anybody else? Postgres. Yes, I bet it rhymes with Postgres, but SQLite is also a fantastic example. Generally in OLTP these days, big data is irrelevant. NoSQL, which was everybody was so excited about, like, hey, we don't need consistency, we don't need real transactions, and I think all of those sort of NoSQL databases, this is the sort of the DB Engine's ranking, and it's pretty hard to see, but kind of Postgres keeps going up, and kind of everybody else is sort of hasn't really gotten too close. Mongo actually has done pretty well, but I think there's just a lot of energy behind Mongo, and for new things, I think people generally are using Postgres. And there's also a class of NewSQL databases that things like Spanner, things like Cockroach, things like Aurora. And it turns out that most of the time you don't have the scale that actually needs that. Postgres is fine. All right, if you're going to pick a data warehouse for a new greenfield workload on the OLAP side, which one would you use? Well, actually, see, we're hoping you'd say DuckDB, but on the other hand, the big data systems are still going pretty strong in OLAP. Snowflake had its IPO in 2020. Snowflake is still going strong, but there are some systems are catching up. This is sort of the DB ranking. You can see that that kind of DuckDB has the same sort of shape of the curve as Snowflake, just translated by a couple of years. And so getting back to that 1 petabyte query, so that petabyte query, processing 1.09 petabytes. The thing that I didn't tell you when I was running this query on stage was that cost $5,800 to run. So we could make it fast, but we couldn't make it inexpensive. And so I think that's sort of one of the key things is like if the way you're scaling is just by doing the same amount of work in parallel, then over time, as you let the size grow, your costs are also going to grow. And there's some point at which people are like, well, I just don't want to pay that much, or it isn't worth it. Maybe I should pre-aggregate. Maybe I should get rid of some of this data. So yeah, it was 1,000 times more work than it would have been to read a terabyte. And so very often, except in rare occasions, it's too expensive to do most of your computations over big data. So, there was another kind of interesting piece, this sort of the outcome of the separation of storage and compute, which is that the key driver of your cost and performance in these big data systems that have separation of storage and compute is the size of the hot data. So if you're querying if you might have a petabyte of data, but if you're actually only querying over 100 megabytes, then that's all the compute you need. So, and that tends to be, the working set size tends to be much, much smaller than the overall data size. And the compute size tends to scale with that size. And then the total data size doesn't matter. Like sometimes people say like, well, I've got this huge data warehouse. And it's like, well, but how much of that do you actually use? And how big are your actual queries? Because the fact that you've got a petabyte of logs sitting on disk doesn't matter if all you're looking at is the last 7 days. And then the data working set size is rarely big data, and that's why it's actually cost efficient and cost effective to do your computations. So what can we do about this? Well, we see sort of the revenge of the single node. So instead of having these multiple independent boxes, you can just have one big box. And over time, the size of hardware has increased by, since I was sort of doing this 100 or gigabyte data set on my laptop, sizes of data or sizes of machines are 2 orders of magnitude larger. So generally, your working set can fit in a single node. And if you're in a single node, you don't have to pay the big data tax. There's not all this coordination overhead. There's not all this complexity. And you can move faster. You can focus on kind of the important things for your application or important things for what you're doing than if you had to build these complex distributed systems. So data size has turned out to be not as big as everybody thought. And cost, running things in parallel doesn't make them less expensive. The petabyte query was $5,000. And as hardware got bigger, we don't necessarily have to pay the big data tax. So today, how big actually is big data? Well, I was talking to the founder of DuckDB Labs yesterday, and he was saying, well, I've been running this like 1 terabyte data set on my laptop. So clearly, kind of a terabyte you can still run on your laptop. And that's pretty huge. That's 3 orders of magnitude bigger than it used to be. And on the server side, roughly kind of, if it's larger than 10 terabytes, there's probably a good chance you'd want to use some big data systems. But so that's also one of the interesting things is that you just wait a little while, and kind of the threshold for what is big data is going to go further and further, because these scaling increases aren't stopping anytime soon. So a little later, we're going to talk with George Fraser, the CEO of Fivetran, who did some really interesting analysis work on this red set data set that kind of showed how much data people were using, as well as there's a Snowflake data set. But one of the outcomes of what he was saying is, hey, 99.5% of these queries could run on a laptop. And then some analysis I did was that only 1 in 500 users run queries that are actually big data. So if you're designing a system for the post-big data world, like what are some different things? Well, instead of like having these sort of like everything runs in the cloud, you can actually do work on your laptop. In BigQuery, we said, hey, if you have big data, you want to move the compute to the data because it's so expensive to move the data. But hey, if you're not doing massive amounts of data, why don't you run that on your laptop? So some small data principles, just kind of things that we've learned. So if latency is important, do the work as close to the user as possible. And so we have actually some Olama. Olama is here. And it's like, hey, if latency is important for your machine learning models and for inference, why do you have to go back and forth to like these GPUs in the cloud? Why not use the GPUs that are local? When cost is important, do the work where it's least expensive. So maybe that's in the cloud, maybe that's on the edge, maybe it's a different region, maybe you can find, but you can actually move the data to where it's effective to run. Simplicity is better than scalability. So kind of, they say in software engineering, premature optimization is the root of all bugs. Kind of premature scaling is kind of the root of all like overcomplications. We've got the Terso folks here who are kind of productionizing SQLite as a great example of that. Simpler is faster. I think this is one of the key things of DuckDB and why it's so fast is like, hey, we're going to start with something simple. We're not going to build this elaborate distributed system, and we're just going to focus on making it great. And then finally, think outside the cloud. It's not just, hey, I'm going to run everything in the cloud. Once you start building these architectures that can combine local, that can combine edge, that can combine some other pieces, you can come up with really, really interesting architectures and really different ways of doing things. And kind of the thing that got me onto this was, when Databricks did this, they just did some benchmarking, and they were bragging about how they had the fastest TPCDS result on a 100 terabyte data set. And Snowflake said, well, you're cheating, and then Databricks said, no, you're lying, and it was just sort of this like crazy fight. But the thing that was hilarious to me was actually that the data size they were using was 100 terabytes. And for my time at BigQuery, literally nobody runs queries that big. Like we had some of the largest customers in the world, and they were using 1 to 2 orders of magnitude on their largest query. And so it said, hey, there's something weird here. So I published this Big Data is Dead blog post. And I got a lot of feedback from that. And it started out with like, no, you're wrong. It turns out actually not that many people said that. And it was mostly sort of Hacker News, which I think they will say that about anything, and a handful of Databricks execs who were convinced that I was on completely wrong. But there was also a lot of people who said, I totally agree with what you said, but like I've got big data. And I think this is the whole like working set versus total data size fallacy. And most of these people probably don't have big data, but I don't want to fight them over it. There's also some people who are like, duh, like big data was never really a real thing. Fine, but I'm happy you agree. Like we can all just agree. And then a handful of people said, thank you. Like this validates the experience that I've been having, and people haven't been saying this, and I'm so glad you're saying this. And so these are our people. And these people are actually what kind of is behind wanting to do this this conference. So why did we come up with this conference? We really want this to be a kind of a collaboration. We didn't want to have a giant event that was like, hey, we can fill a giant auditorium or whatever. We wanted to have really, really awesome, amazing people who would have a great dialogue and have interesting things to say and provide opportunities for them to meet each other, exchange ideas. How many people here are startup founders? There's a ton of startup founders in this room, so a ton of ideas, behind people that are putting together new tools and technologies, and that sort of is super exciting. So with that, I just want to say thank you. Long live small data, And really, we want to hear from you. You know, what do you like about this? And then please do talk to each other after this, and hopefully we can forge some new bonds and build a movement around small data. Thank you.